Okay, hi everyone. Today we're going to be looking at specific heat capacity and their calculation. So first of all, let us look at the definition of thermal energy. The thermal energy or energy gain or loss in a substance is equal to the amount of substance times the specific heat capacity times the temperature change. The temperature change can be either rise or fall. So in symbols, we can write this as E equals to mc into T2 minus T1. T1 and T2 are the initial and final temperatures measured in Kelvin. You can also write as E equals to mc delta theta. So delta theta is change in temperature, which is either rise or fall, which is the same as T2 minus T1. Or you can also write if the temperatures are given in degrees centigrade. So you can write delta E equals to mc delta theta or delta Q. So the symbols for energy is either E or Q. All these equations, they all mean the same thing. You can use any of the equations which you are familiar with. Now, here are some substances with their specific heat capacity. SHE stands for specific heat capacity. So you can just read through it and look through their specific heat capacity. Okay, I take the first question.
We know that energy supplied is equals to mass times specific capacity times change in temperature. So we'll plug in the values. E is equal to the mass 0.20 times the specific capacity 1800 times 50 degrees, which is the temperature rise. So that will give us 180,000 joules. We can convert this to kilogram by dividing by 1000, and that gives us 18 kilojoules. Here, we know that E is equal to mc delta theta. So the energy E is equal to the mass 1.0 times the specific capacity 4200 times the temperature change, which is 10, and that is going to give us 42,000 joules. By dividing by 1000, we have 42 kilojoules. So since the temperature drops from 100 degrees centigrade to 20 degrees centigrade, it means that heat will be given out to the surrounding. Here, E is equals to mc delta theta, that's T2 minus T1. So E is going to be the mass 1 times the specific capacity 4200 times T2 is 20. So I have 20 minus T1, 100. So that is going to be equal to 4200. That's 1 times 4200 times minus 80. 20 minus 100 is minus 80. It's going to give us minus 336,000 joules. The negative sign shows that heat is given to the surrounding. So we can convert this to kilojoules by dividing by 1000. That's going to give us 336 kilojoules. E is equal to the mass is 2 times the specific capacity 900 times the temperature 60 minus 20, that's 40. And when we multiply that out, our result is going to be equal to 2,000 joules. So when we divide by 1000, that gives us 72 kilojoules. E is equal to, here we have to convert the 750 grams to kilograms. So that would be 750 divided by 1000. That's going to give us 0.75 times the specific heat capacity of water is 4200 times the temperature change, 80 degrees minus 20, that is 60. 20 minus 80, that's minus 60. So that's going to give us minus 189,000 joules. The minus sign shows that heat is transferred to the surrounding. So when I divide that by 1000, the magnitude of the heat is just going to be 189 kilojoules. And for question 6, I take a bath with 100 kilograms of water which has been heated from 15 degrees centigrade to 45 degrees centigrade. The specific capacity of water is 4,200 joules per kilogram per Kelvin. How much energy has been transferred into the hot water bath? So E is equal to the mass times the specific heat capacity, 4,200, times 45 minus 15, that is equal to 30. So when we multiply this out, our result is going to be equal to 12,600,000 divided by 1 million. That's going to give me 12.6 megajoules. Come around, E is going to be equal to the new mass, 15 kilogram, times the specific heat capacity of water, 4,200, times the temperature change, which is the same as before, that is 45 minus 15, which is equal to 30. So multiplying that out, I'll get 1,819,000 joules, and on divided by 1 million, I'll get 1.89 megajoules. So for the C part, how much energy has been saved by having a shower? So we subtract 12.6 megajoules minus 1.89 megajoules, and that is going to give us 10.71 megajoules. So that is the amount of heat that has been saved. If you take a shower instead of a bath, what percentage of the energy do you save? The percentage of energy saved is 10.71 divided by 12.61, which is the original energy in the bath, times 100. And this is going to give us, by pressing on the calculator, 85%. Now for question 7, some helium is heated from 20 degrees to 100 degrees. If 520 megajoules of energy have been transferred into the thermal energy store of the helium, what mass of helium is involved? Helium has a specific capacity of 5,200 joules per kilogram per degree centigrade. So the energy supplied is equal to the mass times specific capacity times the temperature, which is T2 minus T1. So the mass is going to be equal to, the mass, okay, we're making M the subject formula. M is equal to E into divided by C into T2 minus T1. So here we'll plug in the values for E, C, and T2 minus T1. So that's going to give us is 5,200. So it is in megajoules. So I have to convert to million times 10 raised to the power 6 by converting to joules, divided by 5200 times the temperature change is 100 minus 20, that is 80. And we'll plug these values into our calculator. We're going to have 1,250 kilojoules as the mass of the helium. Some water is heated by 10 degrees centigrade. If 84 kilojoules of energy have been transferred into the thermal stored energy of the water, what mass of water is involved? We know that M is going to be equal to E divided by C delta theta. That is when we make M the subject of the formula. M is equal to 84 kilojoules. That's 84 times 10 raised to the power 3 joules, divided by the specific capacity 4,200 times change in temperature, which is 10. So I'm plugging this into my calculator. My result is going to be 2 kilogram. Heat 0.20 kilogram of an unknown metal so that the temperature increases by 45 degrees centigrade. I record the energy transfer into the metal as 4.5 times 10 by 5 joules. What is the specific heat capacity of this unknown metal? So the specific capacity is going to be E divided by the mass times change in temperature, which is equal to 4.5 times 10 raised to the power 3 for the energy, divided by the mass 0.2 times the temperature change, which is equal to 45 degrees. So on plugging this on my calculator, my result is going to be equal to 500 joules per kilogram per degree centigrade or per Kelvin. 0 gram of hydrogen is heated by transferring 3.3 times 10 power 5 joules of energy into gas. If the starting temperature is 20 degrees, what is the final temperature of hydrogen? After heating, give your answer rounded up to the nearest 100 degrees. The specific capacity of hydrogen is 143,000 joules. First of all, I have to convert the 1 gram to kilogram by dividing by 1,000. That's going to give me 0.01 kilogram. So by applying the formula, A is equal to mc delta theta. That's delta theta is the temperature change, so we'll make delta theta the subject of the formula. So delta theta is going to be equal to E divided by mc. So on plugging in the values, the heat supplied is 3.3 times 10 raised to the power 5 joules divided by the mass is 0.01 times the specific heat capacity, which is 14,300 joules per kilogram per Kelvin. So if I press this from my calculator, delta T is going to be 23,077 degrees centigrade. So that is the change in temperature. Now we know that change in temperature is equal to T2 minus T1. So here we already know we are going to make T2 the subject of the formula. So T2 is going to be delta theta plus T1. So we'll plug in the values. Delta theta is equal to, or T2 is equal to 23,077 plus T1, which is 20 degrees. So on adding these together, my result is going to be equal to 23,097 degrees centigrade. So we have to round it off to the nearest 1,000 degrees. So the 1,000 is at 23. So we'll round off this value to 23,000 degrees centigrade.